Hello, this is Jack Lee and Loud and Sundling for LAB8 lasers. This is LAB8 for OPTI380A, or TA is around the win. This is the laser lab, which has 4 parts. Part A of this lab was the laser cavity alignment. We began with the green laser and aligned it on the optical axis with the mirror. We then inserted the gas tube and aligned this using the laser and the mirror. Next, we turned off the laser and then turned on the high voltage power supply. And then we fine-tuned the gas tube placement and the mirror until we were able to find the lasing. After this, we added the fiber and observed the different higher order modes as the mirror was moved. We had some issues aligning to begin with, even with Professor Paw's help. But eventually, we were able to find it, and when we did find the lasing, it was still very delicate, and the modes would switch very, very quickly.
The Fabry-Perot spectrometer, we attempted to find the cavity length of the Heaney laser by first aligning the Heaney laser with the beam splitter in the oscilloscope detector. Then we measured the separation of the multi-lobe patterns and calculated longitudinal mode spacing to find the cavity length of the Heaney laser. Moreover, as shown in the setup on the right, we used the Heaney laser in combination with the beam splitter and the oscilloscope detector in order to measure the wavelength versus intensity peaks for the propagation of the laser. Additionally, to find the polarization of the laser, we used a linear polarizer, adjusted the orientation until the intensity of the peaks went to 0. We can see that the cavity length of the Heaney laser was within 6% of the expected value. Moreover, when we put the polarizer on the optical axis, we found the laser polarization to be p-polarized. In the lab, we were required to use the sodium source in conjunction with the Michelson interferometer to find the change of wavelength between two primary wavelengths being emitted. Therefore, after properly aligning the interferometer, we adjusted the micrometer to the end of its scale and then found the first instance of no visible fringe modulation. Then, by adjusting the micrometer, we found 3 more instances of no visible fringe modulation and then used the square of the wavelength of the sodium source that we found earlier in the lab divided by the average modulation spacing of the 4 null spaces to find the difference between the two wavelengths being emitted. Ultimately, we found the difference to be 5.4 angstroms, which is very close to the actual separation of 6 angstroms. Results shows that the central wavelength for the red Heaney laser was around 632.8 nanometers, which is the reported wavelength of the Heaney laser. We also found the mode width to be between 20.3 and 58.3 picometers, while the mode spacing was 0. Moreover, for the red laser diode, we found the central wavelength to be equal to 651.5 nanometers and the mode width to be between 132 and 208 picometers, while the mode spacing was around 0.25 nanometers. In Part D of the lab, we had to use the exact same setup as in Part B. However, instead of using the light directed perpendicular by the beam splitter, we observed the laser light propagating through the double mirror system and onto the detector of our electrical spectrum analyzer. Moreover, when conducting this procedure, we found the graph of the frequency versus power for the red Heaney laser just have one wavelength peak, which made it impossible to calculate the cavity length of the laser. Consequently, we can contribute this error to the beam splitter within our optical system, which could have attenuated the secondary peak enough such that I was confused with noise.